All right, welcome back. All right, so let's get into this. So differentiation of implicit equations. I'm going to start off with something just to help you understand what's going on here. Something is a little simple. So let's do a circle with the radius of 4. Okay, so the equation for a circle with a radius of 4 is y squared plus x squared is equal to r squared. So that's 4 squared, which is 16. And this is the equation that we're going to be dealing with. Now, if I go over here and I graph this circle, then here's my circle. Oh, that's a horrible circle. Horrible. Let's try this again. Alright, so if I go over here and graph a circle, okay, not great, but better. What I want to do is I want to be able to find an equation which gives me the tangent line slopes at any point. So now here, if I look at the circle and I do a vertical line test, then there are 2 values of y for any x. So this is an implicit equation. And what I want to do is, for any x value, I want to find the tangent line slopes. And notice that at a given x value, except for at the ends, there are going to be 2 different slopes for a given x value. Okay, so what I want to do is I want to find the equation for the tangent line slope for the circle. So in other words, what I want to do is I want to find dy dx. Okay, we're first going to do this the hard way, and we're not actually going to be using this hard way. It's not really hard, it's just tedious. And you can only use it with certain implicit equations. So I'm going to call this the hard way, and so we're really not going to use this. But the harder way of doing this would be to break this into a piecewise function. So I'm going to write the equation of the circle as a piecewise. And again, there's only a small number of implicit equations I can do this with. But if I solve for y, so if I go back up here and I look at this equation for a circle and I solve for y, I get y is equal to plus or minus the square root of 16 minus x squared. So I can write this as a piecewise function. Each piece is a function by itself. So I've got y is equal to minus the square root of 16 minus x squared, and that's for y is less than or equal to 0. So if I look at, I'm going to go back and do a graph of my circle. So what this gives you is this actually gives you the bottom portion of your circle. And if I do the other piece, which would be the plus square root of 16 minus x squared, then this is for y is greater or equal to 0, and this gives me the top portion of my circle. And so if you actually put these 2 equations into your calculator, you'll be able to plot the circle. But notice that these are 2 separate functions. There's a function on the top and a function on the bottom. Now, what I can do is I can take the derivative of each piece. And I'm going to do so on the next page. So I'm going to add a page. Okay, and so if I take the derivative of each piece, I'm just going to write this down again real quick. So the piecewise function is y is equal to minus the square root of 16 minus x squared for y less than or equal to 0, and plus the square root of 16 minus x squared for y is greater or equal to 0. Okay, so now if I want to find my derivative, dy dx, then I need to take the derivative of each piece. So up here, if I look at minus the square root of 16 minus x squared, I'm going to have to use the chain rule in order to take this derivative. So I'm taking the derivative of this, look at the top here, this piece right here. And so the derivative is going to be minus, and then I'm taking the derivative of the square root of something. So that's going to be 1 over 2 times the square root of that thing, and that thing is 16 minus x squared, times the derivative of that thing, which is the chain, which is minus 2x. And so if I simplify this out, let's see, the 2 minuses cancel, these 2's cancel, and the derivative is going to be x over the square root of 16 minus x squared, and that's for y values that are less than or equal to 0. And similarly, if I take the derivative of the second piece, which is plus the square root of 16 minus x squared, then again using the chain rule, I've got the derivative of the square root of something. So that's 1 over 2 times the square root of that thing, which is 16 minus x squared, times the derivative of the thing, what's inside, which is minus 2x. And so here the 2's cancel, and I get minus x over the square root of 16 minus x squared for y values greater or equal to 0. Okay, so if I then look at my circle, and let's say I want to find the derivative dy dx when x is equal to 2. So I'm going to go over here and draw my circle. Okay, I'm relatively pleased with that circle. All right, so at x equals 2, so this is 1, 2, 3, and then 4. So when x is equal to 2, notice there's 2 y values here. And I can figure out what the 2 y values are by going back up to my piecewise function. And so if I just put in x equals 2, then this point here is going to be the bottom part of this piece. So that's for y values greater than 0. So that's going to be a square root of 16 minus 2 squared. So that's 16 minus 4. So this point here is going to be 2, and then positive square root of 12. And then the point on the bottom, I'm going to have to use the top of the piecewise function. So if I put in x is equal to 2, I get minus the square root of 16 minus 2 squared, which is going to be minus 12. So this point down here is 2 comma minus square root of 12. So what I want to do is I want to find these two slopes. So the slopes of the tangent lines at these points. And so to do so, I look at my derivative equation, which is right here. And so for the top piece, I'm going to use this derivative here. So so dy dx when my xy is equal to the top point, which is 2 square root of 12, I'm just going to put 2 and square root of 12 into this derivative. So this is going to be minus x is 2, and then I've got divided by the square root of 16 minus x squared, which I know is the square root of 12. And so I've got a negative slope here, negative tangent line, and so that agrees well with that. And so if I look at the derivative where x is equal to 2, but y is equal to negative square root of 12, then I'm going to put this into, let's go back to the derivative equation in the middle of the page. I'm going to put it into the piece for y is less than 0. And if I put in x is equal to 2, then I'm going to get a positive value of 2 over the square root of 12. And this is indeed a positive slope, so that works out. But this is really a tedious process. And again, most implicit equations cannot be broken into piecewise functions. So this is actually not very practical. But I just wanted to kind of show you like how you would do it. And I want you to also appreciate how using implicit differentiation is much nicer and much more efficient. So let's go ahead and do that right now. Let's see one here. All right. Okay. So, yeah, got it. All right. Beautiful. Okay. So the easier way, and this is the way we're going to be doing these. Easier way is to use implicit differentiation. And again, this is differentiation of implicit equations, but people just call it implicit differentiation for short. So what we're going to do is we're going to start off with the original equation, which is y squared plus x squared, is equal to 16. And we're not going to solve for y and make it into a piecewise. We're just going to go ahead and take the derivative of this the way it is. So step one is we're going to take d dx of both sides. Okay, so I'm going to take this equation here for the circle. I'm going to take d dx of both sides. And I'm going to distribute the derivative whenever I have a sum or difference, never a product or a quotient. All right, so I'm going to take d dx of y squared plus d dx of x squared, and that's equal to d dx of 16. Okay, so d dx of 16 is 0, so the right-hand side here is 0. Okay, so let's deal with the left-hand side. I'm going to do the easier one first. So the derivative of x squared, so I've got same, so I'm not going to write the chain because the chain is 1. So the derivative of x squared with respect to x is just 2x, not a problem. Okay, next piece. Okay, so here I'm going to have to use the chain rule. But notice that x and y are different. They're different variables, so I'm going to have to use the chain rule. And it's just like doing the derivative with respect to u in the chain rule before, because I've got two variables that don't match, so I really have to put that chain in there. So the derivative of y squared, so just think of like, okay, I'm taking the derivative of just y squared. So the derivative of y squared, using the power rule, is 2y to the first. But then I need to multiply it by the chain, which is y prime, or I'm going to write it as dy dx. Okay, so I've taken the derivative of dx on both sides. And now for step 2, what I'm going to do is I want to solve for dy dx. And so here I'm going to rewrite this, 2y dy dx plus 2x is equal to 0. So I'm going to subtract 2x from both sides and divide by 2y. So I've got, okay, so there was an error before. I'm not sure where it left off, but it kicked me out. I'm back. All right, so I'll just go up here. So I'm solving for dy dx. So I'm going to subtract 2x from both sides, divide by 2y. And then the 2's cancel. So I get dy dx is equal to minus x over y. And so I didn't have to break it up into piecewise, and I just do it as one single function. And so now, if I'm given a x and y value, so for example, if I'm given the point xy is equal to, let's do 2 comma square root of 12. So if I go back to my circle, that was this point up here. So if I want to find the derivative, then I use this equation, and dy dx at the point 2 comma square root of 12 is I just put in 2 for x and square root of 12 for y, and I get minus 2 over the square root of 12. And so here is that tangent line, and that's the slope of the tangent line. And so here, if you look carefully at the piecewise function, we know that y is equal to, so let's go back to this derivative here. So this y is equal to plus or minus the square root of 16 minus x squared. And so if you put the values in, you can get the same thing as the piecewise function. But once you get used to this, it's a lot easier to use. Okay, so let's continue on to do one more. Add a page and a grid. Okay, all right. So let's say I want to find horizontal tangent lines on the circle. So I want to find the horizontal tangent lines. All right, you're going to be asked to find horizontal tangent lines of a lot of different implicit equations. So remember that horizontal tangent lines occur when the derivative is equal to 0. And as we discussed before, whenever you have a quotient like we do for the circle, there's nothing in the denominator that would cause a function to be 0. So here, or an equation to be 0. So all you need to do is set the numerator equal to 0. So this is the general way of finding horizontal tangent lines for implicit equations. So let's go back to our circle. Okay, now as you can see from our circle, you can just see graphically that there's going to be horizontal tangent lines here and here. But let's use the derivative to prove that. So in the last example for the circle, we found that dy dx was equal to minus x over y. So I'm going to set the numerator equal to 0. And so if I do so, I get minus x is equal to 0, or x is equal to 0. And if we go over and look at the circle, when x is equal to 0, which is going to be the y-axis line, when x is equal to 0, that's where our horizontal tangent lines occur. And if you want to figure out what the y points are, then you need to go to the original equation. So the original equation is y squared plus x squared is equal to 16. So if I solve for y is equal to plus or minus the square root of 16 minus x squared. And so these 2 points where I've got the horizontal tangent lines is if I put x equals 0 in for y, then I get 2 different points where I've got horizontal tangent lines. The first point is x is equal to 0, but because this is an implicit equation, there's 2 y values. There's one down here and one up here. So the positive solution gives the one on the top, and so if I put in x equals 0, I just get the square root of positive square root of 16, which is y equals 4. And then also I get 0, and if I use the negative solution, negative 4. And that tells me the 2 locations of my horizontal tangent lines. Okay, next what we want to do is we want to do the same thing, but this time, not the same thing, sorry, hold on, I was trying to figure this out. It's okay, let's reset, I got this. Alright, so the next thing I want to do is vertical tangent lines. So vertical tangent lines, we've talked about, but we haven't really looked for yet. And so let me draw the circle. And if I draw the circle, you can see that you're going to have vertical tangent lines on the edges here. Now remember that the slope of the vertical tangent lines is where dy dx does not exist, but, this is key, the equation exists. So if I just look at the graph, this equation exists. There's points here, there's no discontinuities, but there is a vertical tangent line. And so if there's a vertical tangent line, then the derivative doesn't exist. But more specifically, what it means is that the denominator of the derivative is equal to 0. So to find vertical tangent lines, you want to set the denominator equal to 0. So let's see how this works for this circle. So I've got, from before, dy dx is equal to minus x over y for the circle. So I'm going to find my vertical tangent line locations. Let's say we're flying blind so we don't know what the graph looks like. I'm going to set the denominator equal to 0. And if I do so, then I just get y is equal to 0. Now this makes sense if you look at the graph, because y equals 0 is the x-axis, and that's where the 2 vertical tangent lines occur. But I want to find the points of this, and for something like a circle I can find the points. What the heck happened here? Alright, so I got it. Alright, so the software program. This is like every time I do one of these videos, it's like I have to do like 3 or 4 takes, so you're like actually watching a take that I liked. So this is a little tedious, but actually I'm getting used to it. Okay. Where were we? Okay, so I found that the vertical tangent lines are at y equals 0. So to find the points, what I'm going to do is I'm going to put this into the original equation. Okay, so my original equation for the circle was y squared plus x squared is equal to 16. And if I put the 0 in for y, I just get x squared is equal to 16, or x is equal to plus or minus 4. So the points where our vertical tangent lines are going to be x is minus 4 and y is 0, and x is 4 and y is 0. And if you look at the graph of the circle, you'll see that. You've got one vertical tangent line at x is minus 4 and y is 0, another vertical tangent line at x is equal to 4 and y is equal to 0. So you're going to be doing this with more complicated implicit equations, but the rules are exactly the same. Fortunately for that last mistake, I now know how to go back to different pages. So for whenever you're asked to find horizontal tangent lines, find dy dx, and we're going to be doing more examples of that, and then just set the numerator equal to 0 and solve for x or y. And if you're asked to find tangent lines, then find dy dx first, and then set the denominator equal to 0 and solve for x or y. And then that will enable you to find those. All right, cool. So we're moving right along, and I'll see you guys on the next video.